Hello everyone. I want to talk a bit more about the strengths of acids and bases, and we will be looking at some qualitative features which show up in some of the decisions we'll be making around this. So as we have talked about already, we can measure the strength of an acid or base by looking at the equilibrium constant when that substance is dissolved in water. So when we look at Ka values, and we'll look at those in more detail here, not today, but when we return to class. When we look at those Ka values, we're measuring the strength of the acid or the base. What this means in terms of the interactions of the molecules is that for a strong acid, we have a weak interaction or a weak attraction between the molecule and the proton. So we're showing that down here for a strong acid. This is a weak attraction, so it's easy to break it. So you almost think of a strong acid as being weak, that you can break that bond. Whereas for a weak acid, you have a stronger bond there, so it only partially ionizes. So when we say strong acid, weak acid, we're looking at, is it a strong electrolyte or a weak electrolyte? And so the more you have of more protons you have in solution, the stronger it is. But that means the bond within the acid itself is weaker. What we'll be focusing on in this mini lecture is why we would have weaker bonds for some molecules. So we'll talk about some general trends in acidity, and we'll look at some specific examples. First of all, the stronger the acid, the weaker the conjugate base. Stronger the acid that is donating the proton, the weaker the conjugate base that is accepting the proton. So when you go from, for example, H2O to OH minus, you're going from, in that case, a weak acid to a strong base. This is related to equilibrium. We'll look at that in more detail as we go through equilibrium in class. We also have a trend related to oxidation number. The higher the oxidation number, the stronger the oxyacid. So we're looking at some examples here. So sulfuric acid is a stronger acid than sulfurous acid. Likewise, nitric acid is a stronger acid than nitrous acid. So both sulfuric and nitric we recognize as being strong acids, whereas the other two are weak acids. We'll see a little bit today about why that is the case. And then if we look at a molecule and we trend from the cation form to the neutral form to the anion form, we also have a trend there. So the cation form, this is always assuming that you do have a proton somewhere in that molecule that can be donated. The cation form will be the stronger acid than the neutral form, but the neutral will be stronger than the anion form. And we looked at the water to hydroxide already. Of course, hydroxide is not going to be a strong acid, but water, we can think of water as being a stronger acid than hydroxide, hydronium being a stronger acid than water. Likewise, we could look at ammonia. The ammonium ion is a stronger acid than ammonia. We normally think of ammonia itself as being a base, but we could even have one of those protons lost to get NH2 minus. That would be a very, very, very strong base. So we have this trend in acid strength based on the charge, so based on adding more protons. The base strength, of course, would be the opposite of that. So going in the opposite direction, hydroxide, stronger base than water, stronger base than hydronium. I want to look at some additional things related to bonding. So first of all, we have this table showing some acids and whether they are weak or strong and their bond energies. And you can see that the bond energy for hydrofluoric acid is much higher than hydrochloric, which is higher than hydrobromic, and that hydrogen fluoride is a weak acid. So hydrofluoric acid is weak, whereas hydrochloric is strong, and we're saying hydrobromic is stronger. They are both strong, but if we were to be able to measure them outside of an aqueous solution, we would see that hydrobromic is actually even stronger than hydrochloric. So let's try to explain this trend in terms of what's going on with the bonding. So there's actually two types of trends going on here. One is that as we increase electronegativity, we're increasing acidity. That should make sense. So something like hydrofluoric acid is a stronger acid than water because you have this basically the proton is sort of hanging out there by itself on the hydrofluoric acid. So that you can imagine something coming along and taking that because the electron cloud is more on the fluoride compared to the way it is in water, where there's a little bit more equal sharing in the water. However, there's another trend that's sort of competing with that, and it turns out can sometimes be more important, and that is the bond strength itself within the molecule. So as the bond strength decreases, the acidity increases, and that's what we're showing here. We're showing the bond energy for these hydrogen halides, and we have a fairly strong bond for hydrogen fluoride because they are small atoms that are connected together. So that bond is fairly strong. As we move down to hydrogen chloride, the bond is weaker, and so it's much easier then to pull that proton apart from the chloride. So that is why hydrogen fluoride is a weak acid, whereas the other hydrogen halides are all going to be strong acids. So that's that particular trend. It's a little bit non-intuitive because you often think of, well, electronegativity, you would think hydrogen fluoride, but the bond strength also plays a part in that. We also want to look at not just the binary acids, but the oxyacids, and we're seeing some trends here. So I want to just take a minute and look at these, and then we'll try to explain the trend. So in the first box, we have oxyacids where you just have one other additional atom besides the O and H. And in each case, the bond is oxygen to hydrogen, and then oxygen also to whatever else is present. So you can see we're showing the difference here is what we're calling Y, whatever that is, and we're showing the electronegativity of Y, and we're showing that going down, and as that goes down, we're seeing the strength of the acid is also going down. So that's one trend. The other trend we're showing here, and we actually have talked about this one a little bit already, but we want to talk a little bit about why this is true. Here we're showing oxyacids that have several oxygens as part of the molecule. So we have HClO4, HClO3, HClO2, and HClO. So we're decreasing the number of oxygens each time. And what we're seeing is that we have a strong bond when we have the most oxygens, and it gets less as we go from there. Okay, so let's go ahead and try to explain these trends. So what we saw was the more electronegative the Y atom, the stronger the oxyacid. So for example, HClO is a stronger acid than HIO because Cl is more electronegative than iodine. And this is, so what we see is basically in a group, the acidity will decrease as we go down that group. And the reason for this is that we're weakening the bond between the hydrogen and the oxygen, and that's the bond we need to weaken in order for the hydrogen, the proton, to be donated. So we're weakening that bond by having something else in the molecule, whatever the Y is, that wants to have those electrons. So if you want electrons somewhere else, it makes it easier to take away the proton. We didn't actually see this one in either of those tables, but it's a similar trend. The higher the oxidation number on the central atom, the stronger the oxyacid will be. So if we look on the periodic table, if we're looking at whatever that Y atom is. And in this case, when we say central atom, we're imagining something where the Y is connected to other oxygens. So as that central atom, the Y, becomes more to the right on the periodic table, the acidity of the that molecule will increase. Again, the same thing. More tendency to want electrons makes it easier to lose a proton. And then finally, the one we looked at in that second table, the more oxygens you have connected to that Y, the stronger the oxyacid. So more oxygens is going to further weaken that HO bond, because you have more electrons that want more things that want electrons. The more things that want electrons, the easier it is to take away the proton. So HClO3, for example, stronger acid than HClO2. Basically, all of these are saying a similar thing, and this is something, if you take organic chemistry, you'll look at in more detail, and that is that the more things want electrons, the more they are willing to get rid of protons. Okay, so here we're showing those trends again. Okay, so acidity is a function of the electronegativity of the Y, with higher electronegative Ys having a stronger acidity. In the second table, we see having, again, more oxygens bonded to that Y increases the strength of the acid, because, again, you have more things that want electrons, pulling those away, making it easier to lose a proton. So that's it. That's all I had for this short asynchronous lecture. If you want, you can practice this here with some examples. I won't go through these right now, but we might come back to them when we come to class. So if you would like to get a jump start on that, go ahead and take a look at these.